Thank you. So thanks to the organizers for giving us the opportunity here to speak today, and thanks to you all for really attending here. It's a great turnout, and I hope I can give you some overview here of liquid cooling solutions and more in general data center efficiency solutions, which we're working on, which we're looking at, but I also want to give a slightly broader overview of what other people are doing in that space. Just as a brief introduction for you, for those who don't know us so well yet, Zenon Systems is a high-performance compute specialist, integrator, reseller. We're based in Melbourne and serving from there our customers around the country, here in Australia, in New Zealand, and also worldwide. We're working in various verticals, including research and education, oil and gas, defense, education, broadcast, and various other areas, and have been doing that successfully for the last 20 years. And that's probably better represented by a short timeline of what we've done over the last 20 years. And just to highlight, maybe because we're here at an HPC event, some of the systems we've installed at CSIRO, for example, where we deployed the first large GPU cluster, which was at that time also in the top 500 and in the green 500 as one of the most power efficient systems. We've been working with NCI and expanded the NCI system a couple of years ago with almost a petaflop of performance. And we've just last week delivered a new system also to POSI at the POSI Center here. In addition to that, we've also worked a lot with other research organizations, both commercial research groups, as well as now companies looking into especially deep learning and AI. And we've seen a lot of adoption and a lot of interest in high-performance computing solutions and, of course, GPU-accelerated solutions in that space. But let's look really at data center efficiency and how liquid cooling can come into that to help us out here. Why do we need to drive data center efficiency and novel cooling solutions? Of course, we want to reduce our power consumption. We want to reduce fossil fuel consumption if we can. We want to reduce the associated CO2 emissions. With all that, we can reduce cost. And if we're working hard enough, hope you're with me, let's try to save the planet. The reality looks a little harsher. If you look at the numbers here of this graph, showing the primary energy consumption here over the last 200 years, starting with really kind of the traditional biofuels, looking at coal, looking at oil, and then up on top somewhere nuclear and all the renewables, we still have a long way to go if we want to save the planet. But it gets worse. The computing requirements are growing tremendously. And they're actually growing so quickly that if we're not careful, and this is a prediction here from a few years ago, that the power consumption from computing will actually outstrip the power production on the planet. That's obviously not sustainable, and that's not going to work, and not going to happen that way. So we really have to look at how can we improve the efficiency of our systems today in the data centers, what we have there, and of course going forward. And there were already a few interesting presentations today alluding to big performance gains which can be made and big power reductions in that space, which we really need if we want to continue going on the path we're on. The current trends and demand are really the big challenges here. If you look at some of the data here from the last 42 years, collected by various groups, including from my alma mater, one of the challenges really is that single thread performance increases, as we can see, is kind of slowing quite dramatically. The number of logical cores in our equipment is going up. Well, that's really how we're keeping the performance gains up and how we keep Moore's law going. Power efficiency gains per core are really becoming slower too, because our power consumption is kind of flattening out, and we'll get to that, why that is. And our single thread performance is flattening out. So really our power consumption per thread is flattening out. But overall, the power per socket is increasing dramatically because the number of cores is going up. So that's a rather scary development. And that's, of course, underpinned by the actual technologies and components which are out there, where you see here on the graphs CPUs and GPUs with the power consumption over time. And we've been somewhere in the range of 120, 150 watts on the CPU side. And right now, in the latest generation Cascade Lake AP CPUs, we're going up to 400 watts per package. And similarly, on the GPUs, we're traditionally somewhere in the order of up to 250 watts, because that was essentially what was feasible based on the power availability in the server systems. We've gone up to 300 watts with the SXM2 B100 modules. And of course, that then scales up as we go to larger systems. If you want to squeeze more performance out of your systems and you look at overclocking, things get even grimmer. This is an interesting graph here from Tom's Hardware, where you can look at the numbers for overclocked CPUs. We're already now on a Xeon workstation CPU. When you drive it from somewhere about 3.7 gigahertz, I think, up to 4.5, we're already going north of 500 watts. We're going here up to 700 watts per socket. So the real challenge is now, we, of course, want more compute. We need more performance. We want to run bigger models. We want to run them faster. But how can we actually keep those running without cooking the systems? That's one part of the equation on the component side. Overall, at a higher level in the data center, we have, of course, similar problems where all of this comes together, where power density per rack increases. And so this is here a projection for 2025, where the power consumption per rack could be. We're typically in commercial data centers now somewhere in the order of 6 to high density racks, or 10 kilowatts probably per rack. The expectation is that we're going up to 20, and there could be somewhere a median of 40 kilowatts per rack. And there are designs to go up to 80 and 100 kilowatts per rack, or let's say per rack unit. And the question is, how are we going to handle that? Of course, at the same time, we need to look at keeping an eye on cost. And if we're looking here, where we're in Australia, we're here in the upper third of power costs, which of course is also a challenge for those who have to run big systems in data centers, either commercially or for HPC centers. So how can we quantify where we're at and what we want to achieve? And a very commonly used metric is PUE, the power usage effectiveness, which is very simply calculated as the ratio between the total facility energy, essentially all the power that goes into an HPC center, divided by the energy that's really used by the IT equipment itself. So if I just look at the ratio between the non-facility and the facility and the IT energy, this is really kind of what I'm interested in. How much energy do I need to actually keep my systems running? And that includes all the overhead of the systems, including power conversion losses, including the cooling, of course. And everyone who is running large data centers, of course, wants to minimize their cost and wants to minimize their overhead in terms of power. And I tried to dig up some numbers where we were historically with that. And that's pretty interesting when we look back at some of the first large data centers where we actually have numbers available from Google and Microsoft, for example. In 2008, they were very happy to have a PUE of 1.2, which at that time really meant that 20% of the power they used to run the IT, they have to add another 20% just to keep the cooling going. And at that time, Google and Microsoft were really proud of those numbers and said, we have the greenest data centers on the planet, and everyone look at us, how cool we are, and let's have a look at where we are typically. And from the US government, there are numbers for typical data centers around 2011, which were at about 1.5, which is still not bad, considering that some really badly designed are running at about 2 or 3 with large overheads and power consumption. And over time, of course, the organization have been trying to drive that down. And when you look at the numbers here, they have made big progress here with Google going down to 1.1, Also a commercial data center by Switch claimed to have 1.18, for example. Facebook then, 2015, at the Prineville data center claimed to have 1.08. And it seems like for large commercial data centers, we're now in the single digits there in the overhead in terms of cooling and overhead of energy. The standout probably here is this Allied Control data center, which is a fully immersion liquid-cooled data center, and I'll talk about that technology in a second, for essentially large blockchain provider, essentially cryptocurrency. And they're running with a power overhead of only essentially 2%, which is quite an achievement. And let's have a look at how we can get there. So all the things we need to include in this are the data center design, the location selection. We'll have a look at that in a minute as well. Of course, the component selection, where it really comes down to how do I select the right components for the workloads I expect to run there. Then also improved component design, where we of course see a lot more offload designs to other components. We see, as we have it already on the phones, ideas about big little designs, where we have now specialized cores to run different workloads to optimize our power usage. Of course, we should also look at developing smarter algorithms. The challenge I see with that is that we want to do more with less, but really doing more with more is becoming cheaper, faster than I'm actually interested in working on my algorithms really hard. But if we want to make this sustainable and have really energy efficient systems in the end, this is something we need to look at and keep in mind. And in the end, of course, it's also smarter load distribution, which can be a big problem in large data centers. And finally, of course, the cooling efficiency. And so I'm going to take a few minutes here to talk really about and focus on the cooling itself. For liquid cooling, there's a lot of options which we can either apply already today and retrofit to our systems and data centers, or which we want to design in, of course, in upcoming solutions. So on the one hand, we can look at in-server solutions with closed-loop liquid cooling or heat pipe and solid conduction solutions, in-rack solutions with liquid-assisted air cooling, Brita heat exchangers, and of course then in data centers with immersion cooling, for example. So let me take a closer look at some of these. So in-server closed-loop liquid cooling solution is something we've been working with for several years. We have a lot of experience in that space, especially for our high-frequency trading servers, where we're overclocking desktop-class CPUs up to 5 and 5.2 gigahertz in industry-standard chassis, which go into data centers around the world. And the only way we can really manage the powers, and when we look at the CPUs we're running, we're also running them at 250 watts or something like this, even though they're really designed at base clocks to something like 170 watts. The only way we can handle that is with closed-loop liquid cooling, where we have a cold plate, which is attached directly to the package. We have the pump assembly on top of that. We're pumping the liquid here through the tubing into a large heat exchanger, where that heat exchanger is obviously the biggest we can possibly fit into the package, where in our case, for a standard 1U rack unit server, that heat exchanger is covering almost the entire width of the system. So that has proven a very efficient way to keep the cooling requirements of the CPUs in check and be able to run them at these high powers. Of course, we can also look at passive cooling solutions. The advantage of that, and we've looked into that a little bit as well, is that we can avoid active parts. We don't have any pumps in there which can fail, and we can cover longer distances, and we can have then also very large condensers for efficiency. And in principle, the idea is the same, that you have a cold plate with the evaporating area here on top. You have the liquid coming through. It evaporates essentially in the tubing here, and then just because of the gas formation, pumps itself then through the heat exchanger. It condenses there and then comes back through the tubing again. And also in some of the OEMs in their commercial solutions, in order to be able to integrate very high power CPUs, but the heat sinks on top of the CPUs cannot be designed big enough. That's also a way to just get the heat from the CPU package into an area where you can have then a larger heat sink, a larger heat exchanger essentially. And so that's already being applied in commercial OEM solutions today as well. Of course, we can also look at retrofitting existing systems. And if you've been to the POSI Center yesterday, or if you're going tonight, there's of course lots of examples there where readout heat exchangers are in use. And we've also equipped the racks we installed at NCI a couple of years ago with the readout heat exchangers, where the advantage is that we can use standard servers in the rack, and then we just have a large heat exchanger in the back, which essentially takes out all the heat from the exhaust air from the servers, and then we can go into facilities plumbing to get the water in and out of the readout heat exchangers. Another interesting solution we installed recently as a temporary solution really is what's called these in-rack liquid-assisted air cooling solutions, where you have the liquid cooling solution in the server. You have then the tubing coming out the back and going into the manifolds, and then the manifolds go into essentially here a 2U unit with a huge heat exchanger in there. And that way, we don't need so many small heat exchangers in the system. We really just need a cooling block and the tubing in the server itself, and I'll have a picture of that in a second. And then we just go into the manifolds and into the in-rack racks. Another option, of course, is to go from the manifolds into in-rack CDUs, which are then connected to the facilities water. And if there is not enough room in the rack, there's actually also solutions which attach to the back of the rack to accomplish the same thing, to go into a heat exchange between the internal cooling loop and the facilities water. And so this is an example of a recent project we delivered to one of our research customers. We've been using high-density half-U servers, so 2U 4-node solutions, where you can see a photo here on the right. We have here the pump assemblies with the cold plates, the tubing that then just goes out and uses one of the PCIe slots in the back, essentially. And here in this case, we were actually able to integrate that with Socket Direct ConnectX 6 Mellanox, ConnectX 5 Mellanox adapters, where we can get this tubing here through in between. And when we did the testing here, the numbers are really quite interesting, that we can, when we ran a CPU limp pack, for example, we were able to reduce the temperatures of the CPU packages by about 20 degrees with exactly this setup and this technology. We also deployed 1U GPU servers with NVIDIA V100 GPUs. And when we run limp pack there, for example, we get slightly better performance with the liquid-cooled solution. The typical power consumption is somewhere in the order of 300 watts. Maximum power consumption, because the GPUs can temporarily go quite a bit higher, are almost 380 watts per package. GPU temperatures, again, 15 to almost 20 degrees lower than what you would have in an air-cooled solution. Of course, the next step is, well, why do I deal with a cold plate and having the tubing? Why don't I just throw the whole system into the liquid itself? And there's, of course, commercial solutions already out there. Also at my alma mater, one of their supercomputers, the VSC3, was deployed with one of these commercial solutions with, let's say, various challenges associated with that. We can chat about that later. What's more interesting is I want to refer to the images here, which are from the Down Under Geo team. If you go to the Sundowner tomorrow, you can see some of these tanks in action. They have essentially, based on the ideas in some of the commercial solutions, designed their own tanks. And what you can see here is these beautiful orange tanks. You have the servers sitting here in what's essentially baby oil. It's really good for your hands when you work there. I can recommend it. And that's essentially a completely passive solution as well. There's a big heat exchanger sitting here on the side with water in, cooling water in and out. And it's really just natural convection which cools the liquid here near the heat exchanger. It flows down to the bottom, distributes at the bottom of the tank, and then gets heated up here over the servers, and then comes out the top. I'll just refer to Stuart's presentation tomorrow and to your visit to Down Under Geo, then you can see all the details there. So they have implemented this at a large scale already in the data center in Houston, but there's also from various other OEMs solutions available based on the same principle. Really the advantage of what we call the single phase immersion, because you're just using the liquid phase of the liquid here. The advantages are you can essentially reduce the number or completely eliminate fans, because in order to get the systems in, you have to take off all the fans, you have to remove essentially all the heat sinks typically, and you then have to update your BIOS to make sure that the BMCs and the BIOS don't go crazy when there's suddenly no fans and they think they're not cooled properly. What's also really nice, and you'll see this tomorrow also Down Under Geo, the data center temperature and the humidity can increase, and they're really comfortable. It's actually really nice and balmy and warm in there. I like working in those data centers a lot better than in conventional ones. And what's really amazing is also that those data centers are completely quiet, except for the switches, which are still largely outside. And I think the Mellanox team is looking into if they can get the switches into the tanks as well. And some of the storage systems, where some of the hard drives don't like it so much when they are in the liquid. But that's another story to look into. Otherwise, it's very, very quiet in there. Overall, a huge power reduction, cost reduction, and what's really interesting is that reliability actually increases, which has to do with reduced corrosion, because now suddenly all your traces, all your cables, everything is essentially in oil. So there's not going to be any oxidation, there's not going to be any corrosion, and I've seen reports from various users who have this technology deployed that they see far less failures and increased component life, which is actually very interesting. As a second option, what you can also get are two-phase immersion solutions, where essentially the idea is that you also have your components in a special liquid, which is much closer to the boiling point. When it gets hot, it essentially boils, it goes into the gas phase, and then you have a heat exchanger up on top where the gases phase then condenses and drips back as the cooled liquid into the bath again. I see a few challenges with that when it comes to the vapor management, when it comes to servicing the systems, but servicing the systems for the baby oil with the baby oil is actually quite a pleasure. Apart from that, let's get a little more radical. Why not put the whole data center in liquid? And so Microsoft Research conducted this experiment, and they have this project going. They call it Project Natick, where they essentially put a whole data center into the ocean. They started out with these smaller tanks. They recently went to version 2 with a much larger tank. And you can see that here on the bottom, you have the cylindrical tank here in the back. You have the custom designed server racks here with all the HPC equipment in the front. And that just slides into the tank. It gets hermetically sealed. You have somewhere on the side then the power in and communications in and out. And the question is, can this be then used as a model to essentially deploy huge, large data centers in much shorter time? So the claim is that these data centers can essentially be deployed in 90 days. You can deploy them very close to urban centers. A lot of urban centers are somewhere near the coast. You get pretty much free cooling by virtue of having the ocean water around you. The only challenge I see is a little bit of servicing. So you might want to have enough redundant equipment in there that you can still leave them in there for a few years until you have to pull them out and replace the equipment. But I've also heard this from vendors at the SC conference a couple years ago when I looked at the two-phase cooling solutions, which are also hermetically sealed because you have the gas and the liquid phase there in that box. And the argument was, well, you just deploy enough of these boxes, and then you just dig a big hole under your golf course. You put the boxes with your servers hermetically sealed in your golf course, put your fairway over it, and don't worry about them anymore. My question how I'm going to replace any components or systems in there went unanswered except for buy more boxes. So I have the same question about the servicing here, but of course for large commercial operators who can then essentially work in the cloud mode and who can live with failing components and then just use other replacement components, such a data center somewhere in the ocean off the coast, ideally then coupled maybe with a wind farm to power the whole system, might be quite attractive. And I'll just want to leave you with a more realistic view of what else we can do to drive data center gains. And I want to give you an example here in a second as well. What we've seen, I think, is very important is that we need to measure everything we can, including power, calculating our POEs, measuring our load, measuring our temperatures and humidities. And then adjust the threshold and sensitivities for the whole data center essentially as much as we can. Increase the humidity range as we can, increase temperatures. A lot of data centers are running at about 20 degrees Celsius, even though the components and the systems could run at much higher temperature. A lot of that also has to do with hotspots in the data center where you need to make sure that even in the hottest area that you have enough cooling there so that your systems don't overheat, which is really a question of the data center design, where it comes down to optimizing the tile layout even and the air outlets to match them with the IT load to exactly avoid those hotspots. Even looking at simple things like blanking plates, side panels, barriers, and even the return air inlets into the crack units in existing data centers actually make a pretty big difference. Of course, using free cooling, well, either in the ocean or in a cooler climate, welcome to Canberra, or if you can put them somewhere near the Arctic Circle. Of course, there's a reason why a lot of the big commercial providers put up data centers in Norway and in Sweden and in Iceland, for example. Even reducing just the light load, paying attention to power conversion, and also to the UPS for the commercial providers is pretty important. And the case study I want to show you is because I find this quite intriguing because it's really a retrofit of an existing system, is here from Google from a few years ago, where they were looking at network points of presence, where they started out with PUEs which were on the order of 2.2 and 2.4 in those 5 different network POPs, which is really pretty inefficient, right? For essentially 100 kilowatts assume of power in there, they need 220 kilowatts to keep the system cooled and keep it running. So the improvements they made are some of the ones which I've mentioned previously, improving the cold aisle and the hot aisle containments, putting on blanking plates, putting on curtains, things like that, which got them from 2.2 to about 1.7. And then in the next step, with new controllers, really running on only one crack unit, improving how the cracks work, they got down to 1.5 and 1.6, which is actually a pretty big improvement. And their return on the investment, which was about $25,000, they had that in within essentially 4 months. They have now savings of $67,000 a year in power costs just to run that network POP after investing only $25,000 in a very, very, very basic equipment. So that's something I think we can all look at and keep in mind as we design our data centers and our solutions. So with that, let me get to the end of my presentation and the conclusion. So I hope I've been able to show you that some of the benefits of liquid cooling, including reducing the fans, reducing the air cooling components, redesigning essentially the whole data center, reducing power and therefore also reducing cost, which can be quite significant for large systems. Where we need more power, we can drive the systems harder, we can drive the CPUs harder and turbo or overclock them. And depending on the design, then we can even get some reliability increases in some of those immersion cooling solutions, for example. I've not talked about some of the other interesting approaches here, of course, with using the waste heat for heating buildings, or using other technologies to convert heat again into power, or cooling technologies like with zeolite and other things, which offer even further gains that can be made. So with that, thank you for your attention. I'll leave my contact details here, and we have a stand outside, so feel free to stop by anytime and have a chat if you have any other questions. Otherwise, I'll open for a few questions now before we break for lunch. Thank you.